Hi everybody. In this video we're going to talk about complex exponential signals. If you're wondering what complex exponentials are, you can see two of them right here. These are the two main functions that we're going to talk about in this lecture. One is a continuous time complex exponential. The other is a discrete time complex exponential. We'll have more to say about that coming up. So first of all, before we get into the details, just a few abbreviations and some notation. First of all, complex exponential, I'm going to say it a lot, so sometimes I'll abbreviate it and even say it CE. So whenever you see CE, that refers to complex exponential, one or the other of these functions, or maybe both. A couple others are continuous time, CT, and discrete time, DT. You're going to get pretty used to seeing this, and I'll try to stick with this throughout. The variable t will refer to continuous time, and t is a real number, so it takes on any value between plus and minus infinity. Whereas dt, discrete time variable, will be n, and it takes on only integer values. It doesn't take on fractional values. It can't be 3.5 or negative 2.5. It can only take on integers, plus or 0, plus and minus 1, plus and minus 2, and so on. So we'll let R, this blackboard version of R, be the set of real numbers, Z is the set of integers, Q the set of rational numbers, and C the set of complex numbers. So once again, this continuous time complex exponential is indicated here. Capital F will be used throughout to refer to the frequency for continuous time complex exponentials, and little f will be used throughout to refer to discrete time frequency. Okay, so first thing I want to point out here is that there are several different kinds of complex exponential signals that we will encounter, and it seems like a subtle difference here, but there's actually some pretty significant differences that we'll see later on. I've drawn some pictures here to illustrate the three different kinds of complex exponentials for continuous time. You'll just have to use your imagination to visualize in your mind what the discrete time versions of these will look like. First of all, the first type is the so-called everlasting complex exponential signal. And it has a domain that is the whole real line. So I've only drawn a piece of it from -10 to 10 seconds here, but recognize that this continues on to positive infinity and extends backwards to negative infinity as well. So that's the everlasting complex exponential signal. There is a causal version, so think of u of t here as the unit step function. So it's 0 for negative times and is equal to 1 for positive times. And so when you multiply a complex exponential times the unit step, you get 0 for negative times, and then you just get the complex exponential signal for positive times. Extending that a little bit further, if we subtract two unit step functions, one time delayed by capital T, we get a square rectangular window or function. So it's going to be 0 for negative times or times greater than t, and it will be equal to the complex exponential between 0 and t. So here I've drawn a picture where I let t be 5 seconds, capital T be 5 seconds. Interestingly, only one of these has a single, or consists of a single frequency, and that is the everlasting complex exponential signal. It's the only one that's drawn here that has only one frequency component. All the others have more frequency components. In fact, an infinite number of frequency components, as we'll see. So for these complex exponential signals, you can derive the discrete time version from the continuous time version through sampling. And sampling works like this. If you replace t, the continuous time variable t, with little n times capital T, so let capital T, think of that as being the sample period. suppose you want to take one sample per second, then t would be capital T would be 1 second. And then n basically indexes the sample. So we refer to n as the sample index, little t is the time index. We'll talk about units in just a minute. But if I evaluate this complex exponential function, the continuous time one, at these sampling times, nt, if you substitute that in, we would have 2 pi capital F times capital T times n. And so the discrete time frequency, little f, is actually equal to capital F times t. A few things to note here, once again, is that in continuous time, t takes on real numbers. The continuous time frequency also can be any real number. In discrete time, the sample index only has integer values, whereas the discrete time frequency can take on any real number. A quick word about units is in order. Continuous time frequency has units of hertz, or cycles per second. That's the number of cycles that a sinusoid passes through in 1 second. In discrete time, if we go back to our formula from the previous page, the discrete time frequency is equal to the continuous time frequency times the sample period. The sample period has units of seconds per sample, and so if we multiply these units together, we end up with the seconds cancel, and we get units of cycles per sample. So the units of discrete time frequency are cycles per sample. So the discrete time frequency tells you how many or what fraction of a sinusoid you will observe in one sample time. So it's worth memorizing these facts that you see here and that we've presented on other pages. So please keep this in mind as we move ahead. And by the way, let me just mention again here, discrete time frequency has units of cycles per sample, and generally it's a fraction. It's a fractional number. What fraction of a sinusoid do you pass through in going from one sample to the next? Another quick word about angular frequency. I personally like cyclic frequency and don't use angular frequency very often, but you can always compute, if you'd like to, the radial frequency or the angular frequency from the cyclic frequency just by multiplying by 2 pi. And you can see how the units work out here as well. I see that I have made a mistake in a little typo here. The units of f are cycles per second, and the cycles cancel here, leaving us with units of radians per cycle. So there are 2 pi radians per cycle, and so we end up with getting radians per second for the units. For capital omega, that's the continuous time angular frequency. Discrete time angular frequency is lowercase omega, and we would have radians per sample because we have cycles canceling here. So 2 pi radians per cycle times cycles per sample, and we would end up with radians per sample. As we'll see in the rest of these slides, I'm going to deal mostly with units of cyclic frequency. All right, now just to set ideas, I have a picture here that I'd like to show which compares a continuous time sinusoid. This would probably, the complex exponential has a real part and an imaginary part that are both sinusoids. So think of this as being the real part of a complex exponential, and this is the continuous time sinusoid. The discrete time version of that is obtained by taking samples, and I let my sample period be capital T equal 1/10 of a second. So whereas up above you see we go from 0 to 1 second here, this is the time axis. When we sample, we're going to sample 10 times in this 1 second because our sample interval is 1/10 of a second. So here I have my sample index. I would have 0, 1, 2, 3, 4, 5, and so on. I could have -1 and so on. So this is the n-axis. And the units of n, if we had to choose units, would be sample index. Okay, and then one other thing to mention here before we move on, we'll be talking about period next. The period for a continuous time sinusoid is just the reciprocal of the frequency. And you can see that this sinusoid passes through one cycle in 1 second, so it has units of 1 hertz. The period would be the reciprocal of that, and so the period is 1 second. Down here below, if you look closely, how far do we have to move to think about the period? How far do we have to move in time before this sequence of numbers repeats itself? And you can see that the answer is 10, because I go from 0 up to 9. That's one period, and then the next period starts here on sample index number 10. So the period of the discrete time sinusoid is 10 in this example. Okay, so what I'd like to do next is shift gears and talk about continuous time complex exponentials and discrete time complex exponentials. And it's surprising how different these two functions behave. By this point in your education, you've probably become very familiar and comfortable with continuous time complex exponentials, and you understand their properties. But to have a good grasp of digital signal processing or discrete time signal processing, it's important to have a correct understanding of how discrete time complex exponential functions behave, and it's very different than the continuous time case. So what I'd like to do is go through a set of about 6 different properties of continuous time complex exponentials and then contrast those with the same property applied to the discrete time case. So the first thing is periodicity, and here we're seeing the definition of periodicity for continuous time signals. A signal is periodic if you can shift it by an integer multiple of this number t called the period and get the same function back. So this periodicity expression has to hold for all t. In other words, you have to have the same function regardless of the shift in the number of periods. And that's what it means to be periodic in continuous time. The same thing holds true in discrete time, where we're calling the period capital N here. And if you can shift by some multiple of capital M, by an arbitrary multiple of capital N, and get the same function back for all indexes n, then you'd say that that's a periodic discrete time signal with period capital N. And let's just observe this comment that I make at the bottom here. The period is always the smallest number t or n satisfying these definitions. And to illustrate that point, let me show you another picture under the document camera. So here we have that same continuous time periodic signal, and you could define the period. Notice that the period here you could define to be 1, but you could also take the period to be 2, because if you shift by 2, then you also get the same function back. But because we've decided that the period will be the smallest number that produces or replicates the same signal through a shift, we'll stick with 1 over f as the period for continuous time signals. Let's take a look at continuous time complex exponential function for just a moment. And let's shift it by some amount, capital T. What we're trying to do here is figure out what is the value of t. Or we could take it alternatively. We could say, what's the value? Let's suppose that capital T is the period, so that this expression holds for all t. Then what we're going to do is derive and figure out, well, what is the frequency then? What must the frequency be? And if we just do a variable substitution into the formula for complex exponential, you can see that this piece here and this piece here appears on both sides of the equation. So we can cancel that from both sides. And then it must be true that this complex exponential is equal to 1. Well, the only way that can happen is if the argument of that complex exponential is equal to some multiple of 2 pi. Well, the only way that will happen is if the product of f and t is an integer. Well, let's suppose that the product of f and t is an integer. Then we can solve for f in terms of t, and then we'll choose the smallest, according to our rule, the smallest number m, which would be 1. And this gives us our frequency in terms of the period. Or we could have done it the other way. We could have calculated the period in terms of the frequency. The important thing to notice is that the continuous time complex exponential is periodic for all frequencies. There are no frequencies that don't give a periodic function. And the period is 1 over the frequency. So let's contrast that now with discrete time complex exponential signals. Here's an example. So let's let x be this complex exponential signal. Let's suppose that n is the period, or that if we shift by n, we reproduce the same sequence for all little n. Well, let's do a variable substitution like we did before. This and this are identical on both sides, so we can cancel those, leaving us with this complex exponential, which has to be equal to 1. Well, we know that this will be the case as long as the argument, the part multiplying j in the exponent, is equal to an integer multiple of 2 pi. So now we have f times n is equal to an integer, or solving once again, f is equal to m over n. So now we have the frequency in terms of the period. It may be the case that m and n have some common factors, and so we can reduce that fraction. And then we get this reduced fraction. So basically here f is equal to the ratio of these two integers. Now the conclusion that we make from this is that the discrete time complex exponential is periodic if and only if the frequency is a rational number. A rational number is a ratio of integers, p and q. And when that is the case, the period of that complex exponential signal will be the denominator of that ratio, in this case q. We'll look at some examples and see what's going on here, but to contrast that with what we saw in the continuous time case. In the continuous time case, complex exponentials are always periodic, and the period is the reciprocal of the frequency. In discrete time, that's not the case. Complex exponentials in discrete time are periodic if and only if the frequency is a rational number, and the period is the denominator in that ratio. The reason this is the case is because in discrete time, the period must be an integer. This capital N value, or q, must be an integer, whereas in continuous time, the period, t, can be any real number. So there's the first difference. Let's take a look at a few examples. Here's the first example, and this in fact is the example that we have looked at previously. Here the frequency is 1/10. That means, and the period is the denominator of that ratio. So here f is a rational number, it's a ratio of the integers 1 and 10, and the period is the denominator. And you can see if you look up here at the sequence, you can see that it in fact does repeat every 10 samples. Let's look at another example. Here is the real part of a complex exponential. The frequency is 3/10. That's a ratio of two integers, so it's a rational number. And so this function is periodic. And the period is the denominator of the ratio. It's 10. And if you look here, if you look carefully at this period that I've highlighted, you can see that indeed this function does not repeat until you pass through 10 samples. There are some symmetries that show up, but you don't get a repeating complete sequence unless you shift by 10 full samples. Let's look at another example. In this example, I have the frequency 9/10. Again, that's a rational number, so we would expect this to be periodic, and it is. The period is 10, and this is the sequence that you get. You might be a little bit curious about this because this looks strangely familiar to us. That's the same sequence that we saw with the frequency of 1/10. And we'll get to the bottom of that mystery later. Here is a sequence, the real part of a complex exponential, and its frequency is equal to the square root of 2 minus 1. Now the square root of 2 is about 1.414. I subtracted 1 from that, and I get this number here. It's an irrational number. Because the frequency is irrational, this sequence is not periodic. It never repeats. It does not have a period. So this is one of the first differences to note between continuous time and discrete time complex exponential sequences, is that discrete time complex exponentials may or may not be periodic. It depends on the frequency. If the frequency is rational, it's periodic. If the frequency is irrational, it's not periodic. You can search this sequence out to plus infinity or minus infinity, and it will not repeat. There is no shift that can be applied that will produce the same sequence. The next property about continuous time complex exponentials that we'd like to look at is uniqueness. And here the idea is if I set two complex exponentials equal to each other and suppose that they have different frequencies, f1 and f2, and then do a little bit of algebra, you can show that the two frequencies have to be the same if these two complex exponentials are going to be the same for all t. And it really boils down to what's going on right here. This exponential will be equal to 1 for all t, provided that the argument is a multiple, an integer multiple of 2 pi. Well, if we set that argument equal to an integer, without the argument without the 2 pi, equal to an integer, you can see that the only way that this expression can be equal to an integer for all t is if f1 minus f2 is equal to 0, or in other words, f1 is equal to f2. They're the same frequency, it's the same signal. The only way you can get different frequencies, or different signals, rather, is to use different frequencies. So that's a familiar concept from continuous time, but it unfortunately does not hold in discrete time. Let's take a look. Let's suppose we have two complex exponential sequences, discrete time, that are equal for all n, and let's set those equal to one another and use a little bit of algebra. We end up with a similar sort of constraint that the argument without the 2 pi has to be an integer. And this expression has to hold for all integers n. Well, fortunately, n is an integer. So as long as f1 minus f2 is an integer, the product of two integers is still an integer. And so what this tells us is that f1 minus f2 has to be an integer, or in other words, that f1 is equal to f2 plus some integer. So what this tells us is that you can have two complex exponentials with different frequencies that give you an identical sequence, provided that the frequencies differ by an integer. This is very strange, and this tells us that discrete time complex exponentials are not unique. Let's move on to the next property. Or actually, this is exploring that same property further. Here I have the frequency axis that I've drawn. And I have highlighted a particular frequency f0 right here. And then I'm also showing f0 plus 1, f0 plus 2, f0 minus 1, f0 minus 2. You could continue this. You could add plus 3, plus 4, and so on. And it turns out that what we've just shown is that if you compute the sequence, the complex exponential sequence, for any of these frequencies, you will get the same exact sequence. There's no difference between these frequencies effectively. Effectively, they're all the same, even though they're different numbers. But when you embed it within the complex exponential sequence, it gives you the same sequence. We call these signals aliases of one another. They have different frequencies, but they give the same sequence, and so we call them aliases. Sometimes we refer to these frequencies as being aliases of one another. They're equivalent. The other thing that's interesting here is that you can go up to higher and higher frequencies, and these higher frequencies are aliased, or they're equivalent to lower frequencies. Everything aliases back to lower frequencies. Because of this property for discrete time signals, we define what's called a fundamental interval. And you could define this anywhere, but probably the two most common definitions for the fundamental interval are to take frequencies between plus and minus 1/2, or to take frequencies between 0 and 1. Notice that both of these frequencies are in length equal to one integer, essentially. And all other frequencies have aliases back in these fundamental intervals. So you pick a fundamental interval, and then you can find, for any other frequency outside that interval, you can find a frequency alias for that just simply by subtracting integers until you get into this fundamental interval. We'll look at some examples in a few minutes. This is another way to visualize things. We've been talking about complex exponentials, and you know that those are complex numbers whose magnitude is 1. So I've drawn the complex plane here with the real axis and the imaginary axis. This dark blue line, the dark blue circle here, represents the unit circle. And we measure, if we were to write down e to the j 2 pi f, that's a complex number that lives on the unit circle, and this shows us the reference direction for positive and negative frequencies. The other thing that's highlighted here is that you can see that as f goes from 0, see this is the point right here, f equals 0, and as we move from f equals 0 up to f equal 1/2, we move around the unit circle over to this point at -1 on the real axis. The same thing holds true as we start at 0 and move around in terms of with negative frequencies. We end up at this same place over here. And so the frequencies get higher and higher and higher between 0 and 1/2 and between 0 and -1/2. But then you can see that the frequencies, we start to repeat the same frequencies again. And so low frequencies tend to be over here, high frequencies tend to be over here, and that's all the frequencies there are. There's no more frequencies than that because of this aliasing property. Frequencies outside this interval alias back into this interval, and so they're equivalent to frequencies that arise just in this one travel around the unit circle. So that's if the fundamental frequency or fundamental interval is -1/2 to 1/2. On the next page here, I'm showing what happens if the fundamental interval is defined between 0 and 1. And here we're going from low frequencies around to high frequencies, and then we go from high frequencies back around to low frequencies as we go from f equal 1/2 up to 1. Remember what we talked about earlier, that f has units of cycles per sample, and that f is typically a fraction. Well, this helps us understand that a little bit better because you can see that we have these fractional numbers between 0 and 1, and that's all the frequencies there are. There are no more than that. Every other frequency that you could write down that's a real number is equivalent to one of the frequencies pictured or encountered on one pass around the unit circle. And that's what I've tried to illustrate here. Here I've drawn the point, this complex number, e to the j 2 pi times 0.2. And that's that point right there on the unit circle. But if you go all the way around the unit circle again, you get to the frequency 1.2. And if you go all the way around a second time, you get to the frequency 2.2. And you can get to 3.2 and so on. But really, those are just traveling around the unit circle multiple times, and you get back to that same point that you could get to on your very first pass around the unit circle. So this is the concept of frequency aliasing, and it's a phenomenon when you're dealing with discrete time signals. The next property that we need to look at is the oscillatory behavior of complex exponentials. And to investigate this, I'm going to put up another picture. Here I have plotted some continuous time complex exponential signals. This first one has a frequency of 1 hertz. The next one has a frequency of 5 hertz. So you can see that in 1 second we go through 5 cycles of this sinusoid. 1, 2, 3, 4, 5. You can see that. And then here I've multiplied the frequency by 5 again. So here we have a complex exponential with the frequency of 25 hertz. And if you counted, you could see that there are 25 cycles of that sinusoid between 0 and 1 second. So the thing to observe is that as the frequency increases in continuous time, the rate of oscillation increases. And this continues on indefinitely for continuous time signals. The higher the frequency, the higher the rate of oscillation, the smaller the period, and that just continues. As f goes to infinity, the period tends towards 0, and the rate of oscillation increases. Let's now think about discrete time complex exponential signals. Here, as we talked about with those unit circle pictures, the rate of oscillation increases for frequencies between 0 and 1/2, and then for frequencies between 1/2 and 1, the rate of oscillation decreases. And so what we find is that low frequencies tend to fall near 0 and 1 and 2 integers, and the high frequencies fall halfway in between integers. 0 is the lowest frequency, 1/2 is the highest frequency, and all these other multiples of, or all these other values of an integer plus 1/2, those alias back to the frequency plus 1/2 or minus 1/2, which is the highest frequency in discrete time. Let's take a look at an example that illustrates this. I've made a plot here showing what happens as the frequencies increase. Now on each axis I've drawn 2 lines. The blue line is the real part of the complex exponential, and the red line is the imaginary part. So the blue is the cosine and the red is the sine part. And I've increased the frequencies. I'm showing the frequencies over here on the y-axis label. So this is a frequency of 0 cycles per sample, and so that gives us just a constant. Over here I've increased it to 1/10. of a cycle per sample. And so you can see that the period is 10. The x-axis goes between about 0 and 30. So you can see that we have 3 cycles of our sinusoid, of this sinusoid, over that interval. Now I'm going to go from 1/10 to 2/10. You can see that the rate of oscillations has increased. Now I'll go to 3/10. The oscillations are getting faster and faster. 4/10, 5/10. That's 1/2. Notice what happens when the frequency is 1/2. The imaginary part is 0, and that's just because we're sampling a continuous time sinusoid right on its zero crossings. Really, underneath this, there's this sinusoidal signal that's oscillating up and down, but we happen to be just unlucky, and we're just taking our samples right on the zero crossings of that sinusoid. The cosine, on the other hand, is sampling at the peaks of the sinusoid. And so in discrete time, a discrete time cosine with frequency 1/2 just oscillates back and forth between these extreme magnitudes, plus and minus 1. That's the highest frequency. And you can see that as we go from a high frequency up to even higher frequencies, the rate of oscillations is not increasing. In fact, it's getting smaller. So you can see that the signal of 1/10 and 9/10, those actually have the same frequency, if you will. The difference is, see, the other thing we could say is that the frequency of this one, we could also say that's equal to minus 1/10. Because 9/10 and negative 1/10, those are different by an integer. And so those are equivalent frequencies. So you can see that for the frequency plus 1/10 and the frequency minus 1/10, what's the difference between those two? Well, you can see here that for negative frequencies, the real part, the cosine, is the same as for positive frequencies, but the sign is actually different. And let's take a closer look at that. You can see that for positive frequencies, the sine wave lags the cosine wave by 90 degrees. But for negative frequencies, the sine leads the cosine by 90 degrees. And that there is the main difference between positive and negative frequencies. For positive frequencies, sine lags cosine, or cosine leads the sine. For negative frequencies, cosine lags behind the sine, or sine leads cosine. That's all there is to positive and negative frequencies. So on this slide, I'm showing the frequency axis for continuous time frequency and for discrete time frequency. And I'm trying to use color gradients to give you the sense about where low frequencies are and where high frequencies are. So you can see here that where we have dark blue, these are going to be low frequencies. And as you get out towards the white part of this gradient, those are higher frequencies. And the higher you, or the further out you move on this axis, the higher the frequencies, the higher the oscillations. But in discrete time, that's not the case. You have low frequencies near 0 and integers, 1, 2, -1, -2. And then halfway in between, we find these high frequencies. 1/2 is a high frequency. 3/2 is a high frequency. And in fact, it's equivalent to the frequency 1/2, because if you subtract 1, you get back to this other frequency. So we could say that 1/2 is an alias of 3/2, or you could say it the other way around. The other thing I've drawn here are the two most commonly defined fundamental intervals between -1/2 and 1/2, or between 0 and 1. This property I'm not going to dwell on, but basically for any time shift in continuous time, you can find a phase shift that will produce that time shift. Or put another way, for any phase shift, you can find a time shift that will reproduce that phase shift. But that's not the case for discrete time. You can find a phase shift that will not, for which you cannot find a corresponding time shift. And that's simply because in discrete time, the time indexes have to be integers. I'm going to skip over some of these slides. The main thing I want you to be aware of is this concept of harmonically related complex exponential signals that are orthogonal. And the idea here is that in continuous time, so what's a harmonic? Harmonically related complex exponential signal. Well, if you define a base frequency f, the harmonics of that are going to be k times f, where k are the integers. And you could talk about the fundamental frequency and the first harmonic and so on. So we could go back through all of that. But essentially, these signals are all harmonically related because their frequencies are all related to a base frequency by an integer multiple. And what does it mean to be orthogonal? Well, if you take the inner product or the dot product between two signals. Now, I know that's maybe not something you're familiar with or comfortable with, but you can define an inner product or a dot product between two functions. And this is one way you could do that. Look back on the previous slides if you want to know more. But essentially, what happens is if you take two different harmonically related complex exponential signals, you can show that they are orthogonal in the sense that the angle between them is 90 degrees. Or if you take the dot product, you get 0. So that's interesting. And then you ask yourself the question, well, how many orthogonal harmonically related complex exponential signals are there in continuous time? And the answer is there's an infinite number. You just multiply by higher and higher integers, and you get a higher and higher harmonic. So there's an infinite number of orthogonal, harmonically related, continuous time complex exponential signals. And in fact, those are the very signals that are used in the definition of the continuous time Fourier series. I've reproduced here the synthesis equation and the analysis equation for the continuous time Fourier series. And these harmonically related complex exponentials are the basis that is used there. We can now go in and define things in discrete time as well, and go through and calculate inner products or dot products. And what we find is that we get orthogonal harmonically related complex exponential signals in discrete time as well. But when we ask how many are there, we find that there are only capital N, where if the frequency, our base frequency is 1 over n, you can find n and only n harmonics for that frequency. And so if we think about the discrete time Fourier series, it's the same type of structure that we have in continuous time, but we have a finite summation instead of an infinite sum, because in the continuous time there's an infinite number of harmonically related complex exponential signals. In discrete time there's only n. So we have a sum over those n, and you can synthesize any periodic signal with period n using a sum of n of these harmonically related complex exponentials. So we'll come back and look at the discrete time Fourier series later. Okay, the next property is an interesting one, and this is one that both the continuous time and discrete time complex exponential sequences have, or complex exponential functions have in common. Let's talk about eigenvectors of matrices, or eigenvectors of linear transformations. So if we, in general, before we get to that, let's just talk about a general vector. So let's let x be a general vector, A be a matrix, a square matrix. And when you take x and multiply by the square matrix, what that linear transformation will do in general is rotate that vector and possibly scale the vector as well. You could be longer, it could be shorter, but it's going to rotate and it's going to scale. That's for a general vector. But there are these special vectors called eigenvectors that when you multiply by a matrix, it doesn't change direction at all. It only changes length. And that's what's depicted here in this diagram that you see at the bottom. I have this vector x, which is an eigenvector of the matrix A. When you multiply by the matrix, you end up getting a vector that's in the same direction as as the x vector that you started with. So lambda here is a scale factor, and all it's doing is lengthening or shortening this vector x. And there are, a collection of these eigenvectors that have this special property that they are invariant in their direction, and they only change in the scale factor when you apply them to this transformation. Let's see what that means about continuous time complex exponentials. What's the analogy? Well, if you take a continuous time complex exponential signal, note that this is an everlasting complex exponential, not a causal or a finite length complex exponential. No, that's not true. You have to stick with the everlasting case. If you put that into a linear time invariant system, well, we'll talk about linear systems and time invariant systems and so on. But I know in previous coursework you've seen continuous time, linear time invariant systems, and you know they obey convolution. Well, if you take one of these complex exponentials and put it in and do convolution, what you find is that what comes out is the same thing that went in. See, we put x into the convolution, and we got x out of the convolution. The only thing that changed is we have this complex number scaling x. And because we put x in and got x out, except for a scale factor, it sort of mimics this eigenvector behavior. And because of that, we call these everlasting continuous time complex exponential signals, we call them eigenfunctions of continuous time linear time invariant systems. And that the magnitude of this complex number tells us what the magnitude changes, and the phase tells us how this complex exponential function has been phase shifted as it passed through the system. It turns out that that same property holds true for the discrete time case. If you put a discrete time complex exponential signal in, whatever its frequency happens to be, there's nothing special about frequency here. It has to be an everlasting complex exponential. But if you put that in and do discrete time convolution, we'll come back, we'll talk a lot about discrete time convolution. We'll talk about the discrete time Fourier transform, so don't worry about that right now. But you put it in and the same function comes out, only modified by a scale factor, which is a complex number in general. And so we call these functions eigenfunctions, or we could call them eigensequences. So let's go through and review what we've learned about continuous time and discrete time complex exponentials. First of all, they behave differently from a periodicity standpoint. In the continuous time case, complex exponentials are periodic for all frequencies. In the discrete time case, they're periodic only for rational frequencies. From the standpoint of uniqueness, all continuous time complex exponentials are unique and distinct if they have different frequencies. In the discrete time case, that's not the case. We have this aliasing concept. Frequency aliases are separated by integers. The rate of oscillation in the continuous time case increases with frequency, but as you increase frequency in the discrete time case, you alternate between high and low frequencies as you scan through the frequency axis. There's a phase shifting property. There's a number of harmonically related complex exponentials that are orthogonal. In the continuous time case, there's an infinite number. In the discrete time case, there's only n. And the eigenfunction property is one that holds both in continuous time and in discrete time. So that's the end of the discussion that I wanted to have. There follows in this set of slides, which can be downloaded from the course website, a set of homework problems. There's about 14 or 15 here, homework problems that I ask you to complete, and we'll talk more about this in class.